Okay, let's get started. Here we go. So you got the current web work is open due Wednesday morning. I'm going to assign another web work based on today's stuff. So you have two different web work assignments that are due Wednesday morning, and then we'll have a short quiz at the beginning of class Wednesday to make sure that you're not only getting the answers correct. I know there's more than one way to get an answer correct on web work sometimes. But you're responsible for the process that we're learning in class, okay? So getting 100 on web work doesn't for sure tell me that you're getting it, okay? So that's what the quizzes are for. You got to show your steps. You know how to solve these basic problems with these different techniques. So any technique is fair game for the quiz on Wednesday morning, okay? So we got a new technique, and it's finding the antiderivative of a rational function. Rational function, what's that? Rational function has the word ratio in it, and that means it's a fraction of two polynomials. So here's an example. 2x squared divided by x plus 1. Always, the first question we always ask is it undoing the chain rule? Could that be undoing the chain rule? 2x squared over x plus 1. No. What small change could you make to this so that it would be undoing the chain rule? What small change would you make to this? It's a really important question because it means that you know how to identify those undoing the chain rule problems, which are the most important ones pretty much. So that question that I keep asking is really important because it's a test to know that you know how to identify that. So what one small change could you make to this so that it would be undoing the chain rule? Okay, what about you? Yeah. Right, in the denominator, if you had x cubed plus 1, then that would be right, and our first attempt would be? So we could change it this way. No, not like that. So if this was x cubed plus 1, then we'd have undoing the chain rule. First attempt would be natural log, right? Natural log of x cubed plus 1 would be our first attempt, and we'd have to clean up the coefficient mess, okay? So that would be that. But it's not that. So what about, and we also talked about with fractions, splitting it up into multiple fractions. What about this one? Can we just immediately just split it up into two fractions and solve 2 1 separately? No, because it had to be a sum or difference, what, in the numerator, right? That's when you can do that. Use the same denominator, and then you have the different numerators, or different terms in the numerator become the new separate numerators. So you can't break this one up. So what we've got is a rational function. It's not undoing the chain rule, and so and we want the antiderivative. Why? Because antiderivative empowers us to actually get a calculation of a net change, right? Because that's what integrals are. Integrals signify, if it's a definite integral with limits, it signifies a net change, and given that rate of change, and then with an antiderivative, we could actually calculate the net change. And that's why we're doing all these techniques for antiderivatives, because it empowers us to find values of net change. Okay, so for this one, for this rational function, here's the first rule. If the degree of the numerator is greater than or equal to the degree of the denominator, we're going to begin by long dividing, and that's what we have here, because the degree of the numerator is 2, and the degree of the denominator is 1, right? The highest power of x. The highest power of x is the degree. So we've got a higher degree in the numerator, so we're going to long divide, and so I'll do that if you've never done that before. And it's just like long dividing numbers. Pretty close. So I use all the same techniques. So we're going to have 2x squared, and then we want to have spots for all the different. So 2x squared is the same as 2x squared plus 0x plus 0. And then we'd also want to do that on that x plus 1 term. If it was x squared plus 1, we would want to write x squared plus 0x plus 1. So we want to show every single power of x in both numerator and denominator. And then just like long division, we're going to say, what are we going to multiply x by to get 2x squared? right? What are we going to multiply x by to get 2x squared? So that'll subtract away. So 2x, and that 2x is going to go in our x to the first column here, right? And why do we do that? Because now when we come down, we multiply 2x squared. Remember long division in what, 4th or 5th grade? Okay, so then 2x squared times x, 2x times 1. And the reason we chose 2x is because now when we subtract this, that goes away, right? So 0, and that's going to be minus 2x. And then again, we ask, what are we going to multiply x by to get minus 2x? Minus 2. So minus 2 is going to be minus 2x. And then minus 2 times 1 is also minus 2. And we're going to subtract. And when we subtract, that will be 0. And we'll get plus 2 is the remainder, right? Plus 2 is the remainder. And so then we can rewrite 2x squared plus over x plus 1 as equal to what? It's going to be 2x, our quotient, or our quotient over the divisor plus the remainder over the divisor. And then just a quick check, we can see that, is that right? What am I doing wrong here? Something's not right. What's that? What am I doing wrong? Because when you add these, you don't get that. Oh, and there's no denominator, right? It's just the quotient plus, yeah, okay, thank you. All right, thank you. Yeah, so it's a quotient. Quotient is basically the answer, right? So we don't want to divide by x plus 1 again. The quotient is essentially the answer to this division, but then we have the remainder, so plus 2 over x plus 1. Okay, so then now this is equal to what we started with. And now this is doable, right? Easy. X squared minus the antiderivative, minus 2x. And then what's the antiderivative of 2 over x plus 1? Should be easy also. 2 times natural log, you should be thinking. X plus 1 plus e. Okay, so that's what you're always going to do first. Now in this case, when we did that, we just got an easy one, and so that's great. All it took was long division. But what may happen is the remaining fraction here will not fit this criteria, but it itself won't be easy. And so that's where this technique called partial fractions comes in, okay? And that's what we're going to do. So what we're going to do the rest of the time is this partial fractions technique. When you long divide, you might still have to do the partial fractions technique on that thing that I circled. Okay? In this case, you didn't. Long division took care of it. Okay? But there's this technique, it's partial fractions, which we're about to do. You may have to do partial fractions on the remainder over the divisor. But in this case, we didn't. Okay, questions? So that's done. We're done with this example. So always check for long division first. Check the degree of your numerator and denominator. If the degree of the numerator is greater than or equal to the degree of the denominator, long divide first. And that might just be all you need, like in this example. But it might not. So let's go on. So now, if you have something like this, if n is less than d, okay? And so there's two conditions here for this partial fractions technique. N is less than d, and d can be written as a product of factors, meaning we can factor the denominator. If you can't factor the denominator, this technique doesn't work. You need to be able to factor the denominator. So, can we factor that denominator? 2x squared minus x minus 1. Okay, this is from 7th or 8th grade, right? What do? Break it up like this. 2x and x. And then to get a product of -1, it's going to be a -1 and a +1. And then how are we going to put those so that we get -x for our middle term? I think we put the -1 here, right? And the +1 here. Does it work? So we start by factoring the denominator. Okay, so now the idea here is partial fractions means we want to decompose this into the sum of fractions. And if it's the sum of fractions, then it can be the sum of integrals. So we'll just start with the sum, right? So the sum of what two fractions is the same as this one big fraction. So we got to think of what do we do when we add fractions together? We have to get a common denominator, right? Common denominator. So what fractions added together would we require the common denominator of 2x plus 1 times x minus 1? Well, that would just be one of those fractions would have a denominator of 2x plus 1, and one of those fractions would have a denominator of x minus 1. So then when we add those together, the common denominator would be the least common multiple of those, right? It would be the 2x plus 1 times x minus 1. So the question is, what are the numerators that now makes that sum equal to our original fraction, right? So we're going to have some constants here, so we'll call them a and b. If we can figure out what the constants a and b are, then we've got an easy integral, right? That wasn't easy before, right? So what are the constants a and b so that we add those fractions together, we get what we started with? What are those fractions a or those constants a and b? Okay, so in order to find that out, what we're going to do is we're going to pretend we're starting with this problem. We're going to add these fractions together. So how would we add these fractions together? Well, get rid of this blinking light. So how are we going to add those two fractions together? Well, we know we're going to need the common denominator of 2x plus 1 times x minus 1. So how do we get that denominator in this first fraction? So I have a over 2x plus 1. What am I going to need to do to this fraction so I get my common denominator, 2x plus 1 times x minus 1? So I need to multiply the bottom by x minus 1, but to keep the value the same, also the top. So this is I'm just starting now. I'm looking at this. I'm saying, how would I add these together to get one fraction? All right, plus. So we got b over x minus 1, and I need to get my common denominator, which means multiply by 2x plus 1, but then I need to multiply the top by 2x plus 1. And so now when I add it, I've got my common denominator, 2x plus 1 times x minus 1. And the numerator is a times x minus 1 plus b times 2x plus 1. So now that is because it's equal to the sum of these, which is equal to the sum of these, which is equal to that. So now these two things are equal, right? So if we get so we're asking what constants a and b make these two fractions equal. And once we know those constants a and b, then we can solve the integral with this form, right? Once we know that a and b. So we got the denominators are fine, the denominators are equal, so we really just got to work on the numerator. So we want 5x plus 1 to equal this numerator, and we got to figure out what a and b are. So we're going to say a times x minus 1 plus b times 2x plus 1 is equal to 5x plus 1. So what are we doing? We're just setting the numerators equal because we got our common denominator. Okay, so what we're going to do is we're going to multiply out. We got ax minus a plus b times 2x plus b times 1. That needs to equal 5x plus 1. So we're going to do this by each power of x at a time. So we're going to look at what's the highest power of x here in this equation. What's the highest power of x? X, right? Power, right? The highest power of x is x to the first. So that means that ax plus b times 2x has to equal 5x. So we're going to gather up, so in our mind, we're going to gather up all the x to the first powers. And then just, actually, all I need to do is look at the coefficients, right? So I'll just do blue triangle. So ax, b times 2x, 5x. And then what's left after the x to the first is constant, right? Constant term. So for constant terms, I have minus a plus b and 1. So I'm going to gather things up by their power of x. I'm gathering things up by their power of x. So those blue triangles, I end up with what? A plus 2b equals what? A plus 2b equals 5. Because they all have an x on them, right? They all have an x on them. All we care about is the a and the b. So if they all have an x on them, we can just pull out the coefficients. A plus 2b has to equal 5. And then similarly, with the red, we got minus a plus b has to equal 1. All right, let me stop and see if you have any questions. Did I lose you? So once we get those numerators equal, we're going to expand it out, and then we're going to just focus on one power of x at a time. So I'm looking at the x, all the ones that have an x with them. I can set those coefficients equal, right? A plus 2b equals 5, and then all the ones that don't have an x, minus a plus b and 1. We good? Follow that? And so now what do we have? We just have a system of equations. System of equations, again, this is like junior high or early high school, solving a system of equations. There are different techniques for this. There is elimination, there's substitution, there's matrix methods. Whatever way you remember and it's going to work. So right away, what do I see in this one? I see in this one that I have plus a up here, and I have minus a. So all I have to do is just add these equations together, and the a's will go away. So that's called elimination, right? Sometimes you have to set it up for elimination. This one is already rigged for elimination. If I just add these equations, I'll get 0a, and then I'll get 3b equals 6, and so b equals 2. And once b equals 2, then I'm home free. I can just use either one of these equations to get a, and it looks like a is, b is 2, that makes 4, and I need one more to make 5. So we got it. We're done, because if a equals 1 and b equals 2 makes this, our original integral here, equal to this one. So I can come down right here like this, and I can say that our original integral is the same as what? 1 over 2x plus 1 plus 2 over x minus 1. And then we got an easy one, right? So what's that? 1/2 natural log 2x plus 1 plus 2 natural log x minus 1. I'm trying to stay out of this lower corner here. Plus c. Okay, if I lost you, please ask. Please ask if I lost you. Anybody? Do you follow everything that I did? So this is called what? The partial fraction decomposition. We had one big fraction, and it's only possible if that denominator is factorable, like this one was. So then using those factors in the denominator, we pulled it apart. And we had to solve for the numerators. Once we got the solve for the numerators, then we could solve it using natural logs pretty easily. Gonna erase it. Last chance. Question. Okay, so let's do another example. Okay, so first question we ask is it undoing the chain rule? No, okay? So it's a rational function, not undoing the chain rule. So now we ask, is the degree of the numerator greater than or equal to the degree of the denominator? What is the degree of the numerator? 2. What's the degree of the denominator? 3, right? Because you have an x and an x squared, that would make an x cubed. So therefore, we've got a degree of the denominator less than the degree of the numerator, which is qualifies us for partial fractions, but the denominator also has to be some kind of factorable form, well, which it is. It's given in this case, okay? So we've got the degree of the denominator is greater, and we've got a factored denominator. Perfect candidate for partial fractions, okay? So here we go. What are we going to do? We're going to write it as a sum of some other fractions here. Now this one is a little different. So we actually need 3 fractions for this. Why? Because I need all possible factors of this that might add together for this common denominator. All right, so x minus 3 is certainly 1. And x minus 2 squared is certainly 1. But this doesn't include another potential factor of this that could be part of this decomposition. So what other denominator do we need? Just x minus 2 by itself, right? So x minus 2 by itself, we might need just a factor of x minus 2. So all these are distinct and possible factors that have that as a common denominator, right? So that's the least common multiple of all 3 of these, and there's no overlap between these three. Like, for instance, we would not need x minus 3, x minus 2. Why? Because that's already taken care of by these two together, right? By these two together. So we would not need that. All right, so now what I didn't mention yet was how we're going to structure these numerators. So far, we just saw that we just had constants in the numerators, okay? The reason that you choose a constant is for the numerator, you're always going to choose a polynomial or an unknown polynomial that's degree 1 less of your denominator, okay? So we look at this x minus 3. What's the degree of that? It's 1. So what's 1 less than degree 1? Constant. Likewise, x minus 2. 1 less than degree 1 is constant. Now, this x minus 2 squared, you might think, oh, that's degree 2, so I'm going to need a degree 1 numerator. But we still consider this degree 1 because it can be factored into x minus 2 squared. So we still, even though the overall degree of that is x minus 2, we have a repeated factor. So all we care about is just the x minus 2 part. So it's still degree 1. So in the next example, we'll see one that's truly degree 2. Okay, this is still degree 1, just raised to a power. But we still consider that degree 1, so then our numerator is still, no, so it's still considering it degree 1. That's the whole point. It's not degree 2. So it's still just another constant, okay? We'll see, in the next example, we'll see one that's truly degree 2, and we'll need a degree 1 numerator. But if you have a degree 1 factor to a power, we still consider it degree 1. So we still just have these constant coefficients for our numerators. But we're going to have a longer, more involved process here because we got 3 to solve for. Okay, so here we go. We're going to have, so rather than write out this intermediate step that we wrote out before, we're just going to look at this and say, if we were to add these together, what would we need to multiply top and bottom by? I've got x minus 3. I need x minus 3 times x minus 2 squared. So what do I need to multiply top and bottom by to get the common denominator? I need x minus 2 squared, right? So that first numerator is going to be a times x minus 2 squared. So more room here. Stay out of this corner. Okay, here we go. And then, so I've got c over x minus 2 squared. What do I need to multiply top and bottom by to achieve this common denominator? Just an x minus 3. So I'll have c times x minus 3. And then, finally, b over x minus 2, and I need to get this common denominator. So it's going to be b times. I need one more x minus 2, and I need the x minus 3. So it's going to be b times x minus 2 times x minus 3. So this is my numerator when I add these 3 together with that common denominator. Right? So I just wrote out the numerator when I add these fractions together using that common denominator, which I'm not going to write out again. We know that that's that. So what does that numerator have to equal? It's going to have to equal this numerator, x squared plus 1. So I bypassed a step there because I just want to think about what we're doing, okay? So again, I'm going to take those 3 fractions and I'm going to change each of the 3 fractions so that it has the common denominator of x minus 3, x minus 2 squared. And think about what do I have to multiply top and bottom by in each one to get that common denominator. So the first one, x minus 2 squared. Second one, x minus 3. And the last one, x minus 2, x minus 3. That has to equal this. Okay, so now we got to expand this. Here we go. We're going to have ax squared minus 4xa plus 4a plus cx minus 3c plus bx squared minus 5xb plus 6b equals x squared plus 1. Check my math. Did I expand everything right? X squared minus 4x plus 4, x minus 3, x squared minus 5x plus 6. Okay, got it. And now we're going to match up powers of x, right? So we'll start with the highest power of x, which is x squared. I'll do blue boxes. So I got an ax squared, I got a bx squared, And I got an x squared here. And I'll do red circles for my powers of x. I've got negative 4xa. I've got cx. I've got minus 5xb. And then what do I have? There's really 0x over here, right? So there's no x term, so it's like 0x. And then finally my constant term, black squiggle, constant, 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 constant. So we're going to match them up. So my x squared equation will turn out to be, the blue, a plus b, any more x squareds, equals 1. Right? Coefficients of x squareds. A plus b equals 1. All right. Then coefficients of x. Those are my reds. What do I have? Minus 4a. I should have left some room for c here. Sorry. Coefficients of x. Minus 4a. Let's do the b here next. Minus 5b. It's like plus 1c, so plus c equals 0. No x's on that side. Are you following what I'm doing? Does anybody have a question? Last equation is going to be for our constant terms. That's my black squiggles. 4. 4a. Any b's? 6b. Any c's? Minus 3c equals other 1. So now I've got to solve this system of equations. Now it's a 3 by 3, 3 equations, 3 variables. We could still do elimination, or we could do some kind of substitutions, or if you remember a matrix method for doing that, you're welcome to do that too. So whatever way you want to, there's different ways to solve a system of equations, whatever way you want. So what do I see here? Let's see. If I look, so this already has c eliminated. You see a plus b equals 1 already has c eliminated. So I could eliminate c from these two equations and get a new equation with a and b, and then combine it with the first equation of a and b. So that's what I'm going to do. So how am I going to eliminate c? I could take this one and do what? Positive, so because I want to add. So if I multiply that whole equation by 3 and then add those equations together, the c's will go away, and then I'll have a new equation of a and b, and I can combine that with the one at the top. I'm going to add those two, and I'm going to get, well, let's see, so this would be negative 12a plus 4a, so negative 8a. Negative 15b plus 6b, is that negative 9b? Equals 3 times 0 is 0, plus 1 is 1. Did you catch it? I multiplied everything by 3, and then I added them together, and this is what I get. Negative 24, or negative 12a plus 4a is negative 8, that's right. Negative 15 and 6 is negative 9, and then 0 plus 1 is 1. So now I can combine these two. And let's just, for something new, let's do substitution now. So I've got what? I've got this one. And I've got this one, the boxes. And I can come here and I can say, this says that A equals 1 minus B. So now I'm doing a different method. I'm doing substitution to solve that system in the boxes. A equals 1 minus B, so I can take the 1 minus B and plug it into this one. Take this 1 minus b right here, plug it in for a in here, and I'll have equation just of b. So I'll have minus 8 times 1 minus b minus 9b equals 1. right, so what do I have? Negative 9b and positive 8b is negative b. Negative 8 minus 8 is 1. So is b negative 9? I think that's right, and that agrees with what I had before. And that means now I can come to very easily to this one, a plus b equals 1. If b is negative 9, that means a is positive 10. And if a and b are 10, negative 9, I could use either one of these equations down here to get c. So if I use this one, I'll get c equals negative 5. So what? So for the b equals negative 9, I just came back to this equation to get a. And then once I have a and b, I came to this second equation. I plugged in my a and b and solved for c, which was negative 5. Anybody have a question on that? So now we got it, right? Because now we have those coefficients up there. So this is a equals 10, c equals negative 5, b equals negative 9, and those are three easy integrals. 10 over x minus 3, negative 5 over x minus 2 squared, negative 9 over x minus 2. So it's going to be 10 times natural log of x minus 3. And then minus 5 times natural log? No, it's x minus 2 squared in the denominator. So I'm going to do what? I'm going to raise power. I'm going to do x minus 2 to the minus 1. So, and then we think about taking the derivative. Do we get exactly that? So I need this to be negative in the end. Right? I need that whole thing to be negative, since negative 5 over x minus 2 squared. Right now, when I do the derivative, it's going to be positive, right? Negative 1 times minus 5. So I just need to change that minus to plus. And then minus 9 natural log x minus 2 plus c. Answer. Questions? Yeah, please. Doing what? Okay, so yeah, so why is it x minus 3, x minus 2 squared? Because we need every distinct factor that has this as its common denominator. So we need an x minus, so we need all powers of x minus 3 and all powers of x minus 2, basically. So there's just one x minus 3 to the first, and then all powers of x minus 2. So we need x minus 2 and x minus 2 squared. Nope. Because it's possible, you need all possible ones, because it's possible that, so like this is an example. You can't split it into 2 because you need minus 9 times minus 9 over x minus 2 to be part of that fraction. If you split it up into 2, you won't be able to solve this. You need all three. We have different, see, we got different factors for all three of those. So you've got to have every possible factor. If we didn't do that, if we just did the first two fractions, for example, we wouldn't have got a solution. It wouldn't have worked, because in order to, the decomposition of that thing includes a fraction that has just x minus 2 as the denominator, as we see, minus 9 over x minus 2. 3. Okay, so suppose this was 3. Then what would we need? We need 1 x minus 3. Then we need 1 with x minus 2 to the first, 1 with x minus 2 squared, and 1 with x minus 2 cubed. Every power of x minus 2. Does that answer it? It's what now? All right, so suppose that x minus 3 was to the 5th. All right, how about if it was x minus 3 to the 5th, x minus 2 squared? Then we'd need 5 fractions that have x minus 3. We need x minus 3 to the first, to the second, to the third, to the fourth, to the fifth, and then we need the 2 fractions, the x minus 2 and x minus 2 squared. So that would be 7. We need 7 fractions. Yeah. You won't have to do that. Well, you'd have to do just that. You might have to do just that, just the first step. Like, what would that? And then you would stop. Okay. So what I just said verbally would be responsible for, but then solving it, no. Okay, let's do one more. Questions on this one? Okay, so what do we ask? Is it undoing the chain rule? No. Is it? And we've got a rational function. Is the degree of the denominator greater than the degree of the numerator? If it's not, what do? We long divide first, right? If the degree of the numerator is equal to or greater than the degree of the denominator, long divide first. But we've got a degree of the denominator is greater. And what else has to be true in order for us to do partial fractions? The denominator has to factor. If the denominator doesn't factor, we can't do partial fractions. That's the whole point. We're decomposing it based on the factors of the denominator. If the denominator doesn't have it, can't be factored into at least 2 factors, you can't do this. So how does this factor? X cubed plus 4x. I'm going to pull this apart. X times x squared plus 4. If you can't do that step, you can't do partial fractions. If the degree of the denominator is not greater than the degree of the numerator, you're not doing partial fractions. Those are the 2 criteria you need. Degree of the denominator is greater, the denominator factors. You need both those things. Okay? So now we've got what? Something over x and something over x squared plus 4. What's the degree of x? Degree of x is 1. And so what we choose in the numerator is always 1 degree less. 1 degree, an unknown representation of 1 degree less of x, which is just a constant. Now, x squared plus 4. Is that some linear thing squared? Right? Like before, we had x minus 2 quantity squared. We considered that to be degree 1. So can that be factored into, say, like x plus or minus something squared? Answer is no. So this is truly degree 2, unfactorable degree 2. So what's 1 less than degree 2? Right, so we can have bx, but there could also be a constant too. So we need every possibility. So we're going to have bx plus c. Bx plus c, which is a polynomial of degree 1 less than degree 2. Now, the rest is the same. So you try to solve this one. Go, see if you can finish it. The rest is the same. Okay, check your work. I put it up there. Check and see how you did.